Dear friends of crystallography around the world, welcome to my poster, Capillary Crystallization, a versatile tool for chemical crystallography and absolute configuration determination. My name is Niels, and I would like to show you some details of my poster. As you might know, growing single crystals suitable for X-ray diffraction is a limiting factor for structural investigation of molecular compounds. If the compound is liquid under ambient condition, conventional techniques such as solvent evaporation are not applicable. In many cases, however, neat liquids form crystalline solids upon cooling. This is now shown by the example of lipidin. Phase transitions can be quantified by low-temperature differential scanning calorimetry, and the information gained can then subsequently used for optimal crystal growth conditions. Once the phase transitions are known from low-temperature DSC, one can start with the preparation of the crystal growth. The pure compound is transferred into a very thin glass capillary and then placed on the goniometer head of the diffractometer. At first, you will only see diffuse scattering related to the amorphous glass capillary. If you start cooling and if you lower down the temperature below the solidification temperature, you will see a polycrystalline powder pattern. To grow single crystals, the capillary is now partially moved out of the cold gas stream to allow the solid to melt again. When the movement is reversed and when the melt is drawn back into the colder region, the remaining microcrystals act as seeding crystals for the growth of larger crystals. After several cycles, and in many cases, very high quality crystals can be obtained. The advantage of this method is that only a very small amount of sample is required, perhaps 5 milligrams of the compound, and that it can later be reused for further studies. This method has been successfully applied to a broad variety of compounds. Combined with advanced refinement strategies such as Nosferatu, capillary crystallization provides highly accurate crystal and molecular structures. Please let me now show you some examples. At first, on the left side, we see the crystal structure of acetic anhydride, which has been unknown since 2016. The method is further applicable to very high reactive compound, such as air and moisture sensitive organoaluminum compounds. It was later discovered that the method is suitable for determining the absolute structure. This has successfully been demonstrated by investigation of a natural product, here on the right side, the gamma-decalactone, as well as with a product of an asymmetric catalysis. I would like to acknowledge Richard Goddard and Michael Patzer for support and insightful discussion. I would like to thank the Max Planck Institute for Kohlenforschung for making this research possible. And also I would like to thank Michael Felderhoff for providing access to the low temperature DSC instruments. If you are interested in this topic, please do not hesitate to contact me under the given webmail address or on the conference in person. Finally, I would like to thank you for your kind attention, and I hope to meet you in person at the conference. All the best.